All right, let's summarize what we've learned about the characteristics of circles, lines, and roses in polar form, all in this handy-dandy chart to help you keep things organized. So here we have our three different equations of circles. R equals A cosine theta, R equals A sine theta, and R equals A. So A cosine theta, we know that A is equal to the length. You know what, rather than write this out, let's just draw a diagram to show this. So R equals A cosine theta. What I want you to be able to do is to sketch that this is A, and it's to the right like this. And if A is less than 0, then it's going to go in the opposite direction. Now, we'll talk about the period in just a minute. If we have sine, then we're looking at a graph that has a vertical line of symmetry. So here my line of symmetry is this line right here. Now my line of symmetry is this line right here. And A is going to be this distance right here. And if A is less than 0, then I would have a graph that goes on the lower half of the graph grid like this. Now the period is how long it takes, what angle it takes to get the entire graph. So remember that when we were graphing this, all I had to do was go around half of a cycle on the rectangular version of the graph. So in other words, from 0 to pi would give me the whole graph, and then it started to repeat itself. So the period is pi, or 180, and then it starts to repeat itself. So remember, the period of a cosine or sine function in rectangular form was 2 pi or 360, but that's not true for the circle here because it just repeats itself after half of the cycle of the rectangular graph. Now, for R equals A, it's centered at the origin, and this is A. It's the diameter. Now the period here is actually 2 pi because to get all of the angles, all of the R values for all of the angles, I would need all 2 pi or all 360 degrees. Now let's look at characteristics of lines. R equals A secant theta. Secant corresponds with cosine, so cosine is going to give me a horizontal line of symmetry, which means my line is actually going up and down. So if I have A greater than 0, this would give me the line over here where this distance is A. And if I have A less than 0, then I would have a line to the left where this is A, because now A is reflecting it the other direction. Okay, so A is going A units in the opposite direction. The period of this graph to get both positive and negative values for A does turn out to be 2 pi or 360 degrees. Notice that the line of symmetry is still horizontal for a cosine graph. The secant goes with cosine. It's the reciprocal of cosine, so it still has that horizontal. It looks the same on each side of a horizontal line. Cosecant goes with sine. It's the reciprocal of sine. So when we also can think of this as secant goes with x, or cosine goes with x, and this is the line x equals A. Okay, that's what we actually get. We get the line x equals A when we do this. Now, when we do cosecant, we get a line that is either horizontal above and above the vertical axis, the horizontal axis, or we get a line that is below if A is negative. So A greater than 0, A less than 0, and once again this distance from here to here is A. And these correspond to the lines y equals A in rectangular form. Period of the graph to get the whole thing, 2 pi or 360. Now this last type of graph is not a function in polar form. Just like x equals a is not a function in rectangular form, because for every value of x there's an infinite number of y values. Here, for every value of theta, there's an infinite number of r values. So if we are graphing this, this is going to be a line that goes through the pole where this angle is a. Theta is equal to a. So whatever theta is equal to is the angle, and it's just every point with both positive r or negative r that's on that line. So not a function, because each theta has an infinite number of r's, of r values. Period, I would need, there's only one angle, so the period is really not applicable here, because you just have one angle in the function. Okay, let's take a look at our roses now. In roses, we introduce that extra parameter b. So the center of the rose is at 0, 0. Okay, so we always have it centered there. We're always coming back to that as we loop through all the petals. The length of the petals is just a. Not hard there. Not terribly difficult. Number of petals, if b is even, is 2b. If b is odd, is just b. The period, how much does it take to get through all? Well, to loop through all of the petals, we need the entire cycle of 2 pi to get through all of the petals. Actually, I need to correct this. The period is actually pi here, because then the petals repeat. Remember, they land on top of each other, which is why we only have half as many petals. So we only really need to go halfway through the cycle to get all 3 petals, but if we go 2 pi, the petals plot on top of each other. Then a couple other things to remember is if a is less than 0, then the petals flip to the opposite quadrant. And if b is less than 0 for sine, the same thing happens, because it's an odd function. For cosine, nothing happens if b is negative. Okay, tip of the first petal. Let's look at an example. We have r equals, say, 3 sine of 3 theta. So we know that the longest the petal can be is 3. And r is going to be 3 when sine of 3 theta is equal to 1. Because that's the biggest that a sine value can be. Well, sine is going to be, sine of 3 theta is equal to 1 when 3 theta is equal to pi over 2, because I know that that is the tallest part of the sine graph at pi over 2. So when 3 theta is equal to pi over 2, then we're going to have our highest value. So that means 3 theta equals pi over 2 when theta is equal to pi over 6, because I would have to multiply both of these sides by 1/3. So when I have 3 theta here, theta has to be pi over 6 for the tip of the first petal. So in general, when b theta is equal to pi over 2, which means theta is equal to pi over 2b. So when theta is equal to pi over 2b, that's when we have the tip of the first petal for sine. Now for cosine, easy. The tip of the first petal is at 0. Okay, because cosine of 0 equals 1. So it doesn't matter what b is, as long as theta is 0. So b times 0 is always 0. So whatever b is, it doesn't matter. We're always going to see the tip of the first petal at 0. Now, of course, this is assuming that a is greater than 0. If a is less than 0, remember all the petals flip to the opposite side. So we're talking about if a is greater than 0, this is where the first petal is. So if you do have to graph something where a is negative, start about thinking about where the petals are when a is positive, like make little dots to show where they are when a is positive, and then just flip them all. That's the easiest way to do it. Now rotating polar graphs. So if I have any polar function, so r is equal to, so we'll just look at this as an example, 3 sine of 3 times, and then in parentheses, theta minus pi over 4. So when we subtract, this is a positive rotation of pi over 4. So the entire graph, every petal rotates pi over 4. If we had, for example, r equals 5 cosine of theta plus pi over 6, this would just be a circle that we're adding. This would be a negative rotation of pi over 6. So whatever we do to theta, okay, if we add or subtract something directly to theta in the equation, that will rotate the graph. Now, there are a couple of advantages of graphing in polar form. One of the advantages of graphing in polar form are some figures have simpler equations. So, for example, the circle r equals 3, which is a circle in polar form. In rectangular form, it would be x squared plus y squared equals 9. Okay, so that would be the same circle in rectangular form, and using in our conics unit, that's the way we would graph it. Much simpler, r equals 3. Number 2, some figures that aren't functions in rectangular form, like a circle, for example, because a circle is not a function in rectangular form. It doesn't pass the vertical line test. Some x's have more than one y. Example, circle. Are functions in polar form. And number 3, much easier to rotate graphs in polar form. In rectangular form, it's actually very, very difficult to rotate a graph. The algebra involved in the equation is very complex, but in rectangular form, all you have to do is add or subtract an angle to theta in the equation, and that rotates the graph. Very simple. Now, it will only rotate around the origin doing this, but it's still much simpler to rotate. And there are some interesting applications of polar graphs. One of the ones I can think of off the top of my head is that the direction of sound from different types of microphones takes the shape of a polar graph. And that kind of makes sense because when we think of a polar graph is emanating from a center point. And so in a microphone, you've got wherever your microphone is, your speaker, your that's where the sound is coming in, and it's going out in lots of different directions depending on the acoustics of the room and the type of microphone. And we'll probably have a video on that later.